Okay, so let's talk about matrices and linear systems. So, of course, we can take a linear system like this and we can just store the coefficients in a matrix. So, I put 2, 3, and I guess 1 isn't really a coefficient of any variable because there isn't a variable attached to it, but we put this vertical line and the right-hand sides of the equations we put on this side. We call that an augmented matrix when it actually has like the right-hand sides of the equation. A non-augmented matrix just wouldn't have this. Anyway, of course, this stores all the important information about the linear system, and it's less writing, because I don't have to write the x and the y and all that. I can solve it in matrix form, and it's basically equivalent to what we already did when we were writing the x and y and all that stuff. So, what would I do? I want to eliminate x. In other words, eliminating x from one of the equations means I want a 0 in the x spot. Like this is the x spot. Like this column is the x spot. So I try to get a coefficient of 1 on top, so I can just swap the two rows. That's like swapping the two equations. I can get this. And then what would I want to do? I would want to subtract a multiple of this row from this row, because that's one of the operations I can do. I can subtract a multiple of an equation from another equation, but I'm looking at a matrix now, so I just call these equations rows. Anyway, so I do this one minus 2 times this one because I want to get a 0 there, and I get this, and then I can read the solution off, right? This row is telling me the equation 0x minus 1y equals negative 3. So I can write that down, solve it for y. This row is telling me 1x plus 2y, and at this point I know that y is 3, so I'll just write 6, equals 2. And so I solve for x. Okay, so it really just accomplishes the same thing with a bit less writing. Alright, so a linear system we call homogeneous, and this is a different use of the word homogeneous than we were talking about homogeneous differential equations, of course. A system of linear algebraic equations is called homogeneous if the right-hand sides are all 0. And when I say the right-hand side, I'm always visualizing it like this, where all the variables are on the left and the right-hand side is just a number. So if those numbers on the right-hand side are all zeros, in other words, the augmented matrix would look like this. So I have this vertical line, and these are all the right-hand sides, and these are all zeros, and the left is just whatever, so I just scribbled. That's what we call homogeneous, when it's all zeros over here. Of course, and this is just a slightly more general fact than something we talked about the other day, a homogeneous system always has one solution, and that's the solution where all the variables are 0. Because if all the variables are 0, then all of these equations are just saying 0 equals 0. So they're all going to be true if I set all the variables equal to 0. So in general, a linear system might have no solution. But if it's homogeneous, it always has at least the solution where you set all the variables equal to 0. It might have even more solutions, but there's no way that it just doesn't have a solution. It always has the one solution. Okay. So here's an example, and we use to illustrate something. We have a matrix that's telling us a system of linear equations, and we're going to express the solution using vector notation. So I didn't want this to turn into a lot of unnecessary work, so I gave us a matrix where the system is already in echelon form, right? The leading variables are like here, here, and here. Like this is the right, or the leftmost non-zero entry in the row. And then this is the leftmost non-zero entry in this row, and then this is the leftmost non-zero entry in this row. And right, it's in echelon form because like this one's to the right of this one and this one's to the right of that one. Anyway, let's solve it. So here's what I do. Some of the variables we're going to call leading and the other ones we're going to call free. And by the way, let's say the variables are x1 through x5. So this is like the x1 column, x2 up through x5. So which variables are leading? They're the ones that are leading in some row. So x1 is leading in this row because of this one. x2 is leading in this row because of this one. And in this row, I would say, so this is x1, x2, x3, x4 is leading. And anything that isn't leading, we call free. So say x3 was not leading, and there's also an x5 which was not leading. Oops. So here's how we're going to do this. The free variables, we're going to say they can be anything. Typically, we introduce some new letters. I typically go to like the letters S and T. They're thereabouts in the alphabet. So let's set each free variable equal to its own S or T. If I had more free variables, then I would go like U and W and so on. And then we can solve for the leading variables in terms of the free variables. So say I can take the bottom equation. So this is 0x1, 0x2, 0x3, 1x4, minus 1x5. So x5 is t, so I'll write minus t equals 3. So x4 is 3 plus t. Okay, I got that off the bottom equation. Let me do the middle one. This one tells me x2 plus 2x3, and x3 is s, 0x4 plus 3x5, and x5 is t, equals -1. Okay, so x2 is -1 minus 2s minus 3t. Okay, top equation. x1, no x2s, minus x3, so I write minus s, and no x4s, and then plus 5x5, which is t, equals 2. Solve for x1. 2 plus s minus 5t. Okay, so what do I mean by expressing all solutions using vector notation? Here I'll show you. Here is a vector. I'm writing it vertically. Let me write what I know. So x1 is 2 plus s minus 5t. x2 is -1 minus 2s minus 3t. x3 is just s. x4 is 3 plus t. x5 is t. So maybe I could leave my answer just like that, but let me actually write it in a couple different ways because I'm trying to emphasize something here. Of course, I can split this up. So let me write any constants like 2, -1. This one just has a 0. This one has a 3. This one has a 0. And then let me write all the S parts. This one doesn't have an S part, and neither does this one. And let me write all the T parts. T, T. This one has no T part. This one just has one T. This one just has one T. And finally, let me factor S out of the S part and T out of the T part. I could probably do that in one step, but I just wanted to be understandable. So if I pull an S out, this is 1, -2, 1, 0, 0. And then -5, -3, 0, 1, 1. Okay, so we're going to come back to that, but let me call that my answer for this. So before I say what I was going to say, let me tell you what a homogeneous, or I guess I already told you what the homogeneous system is. If I give you any linear system, I can make the associated homogeneous system. Of course, a homogeneous system is supposed to all have zeros on the right. So if you give me one that doesn't have all zeros on the right, the associated homogeneous system is just you replace all the right-hand sides with zeros. In other words, if I take the previous example, this is not homogeneous because it's not all zeros here. What I have written here is just the associated homogeneous one. I just copied this down exactly as is, and I replaced these numbers with zeros. And I can watch me do the same thing here, and I'll try to go faster. So, right. What's leading and what's free does not change at all because these left-hand sides haven't changed at all. So these are free. Any free variable gets assigned like an S or a T or a U if there's more of them. So, and this is exactly as it was last time. So x3 and x5 get assigned S and T. And then the rest we solve for them. So let me try to go faster here, and I'll go top to bottom. X1 is going to be given by this equation, and I'm just going to imagine moving these to the other side. So this one's S, this one's T, so this is S minus 5T. Solve for X2. X2 is, I'm going to just move these over. So this is a 2S and a 3T, but I'm moving them over. So negative 2S minus 3T. And then finally, here's X4. This is a minus T, but I'm going to move it over. So X4 is just T. And then I can jump to an answer similar to this. Let me do it quickly. My S part, I'm just going to take all the coefficients of S. That's 1, -2, 1, 0, 0. My T part, -5, -3, 0, 1, 1. Okay. Now that was kind of repetitive, and there's a reason for that. That's exactly what I was illustrating. So what I'm illustrating is this fact. The general solution to any linear system, and when I say general solution, I mean like a formula like what we just came up with that expresses every possible answer. Like this is a general solution to this system, this is a general solution to the associated homogeneous system. So that's what we're talking about. And what this is saying is the general solution of a linear system can be written as P plus H, and these are vectors, so they have hats on them, where H is any solution to the associated homogeneous system, and P is a particular solution to the original system. It could be any particular solution to the original system. So let me talk about what that means in the context of the examples we just did. This is the general solution to the associated homogeneous system. This is the one that we did just now. This is the solution, or yeah, down here is the solution to the one we did before that, the non-homogeneous version. And what you'll notice is parts of it are exactly the same. This has an S part, and it's the exact same vector. Again, like this and this are the exact same. Likewise, there's a T part, and this are the exact same. So basically, this is my H in this theorem. My P is this, that this is a particular solution to the non-homogeneous equation. And let's actually check that it's true. I'm claiming that this represents a particular solution to the non-homogeneous equation. In other words, what x1 is 2, x2 is negative 1, x3 is 0, and so on. Well, if I plug that in, that's telling me, oops, yeah. So this is telling me, actually, maybe I'll do this. This isn't that terrible. X1 is 2, so I plug in 2 there, I've got a 2. And then this is 0, so the negative 1 doesn't matter. This one is 0, so this negative 1 doesn't matter. This number is 0, so the 3 doesn't matter. This number is 0, so the 5 doesn't matter. And I just get 2. So my first equation is satisfied. Likewise, you can check that the second equation is satisfied, because this tells me like 0 minus 1 plus 0, 0, 0 equals minus 1. And the third equation tells me 0, 0, 0, and then 3, and then 0 equals 3. So, sure enough, this is a particular solution to this. Maybe an easier way of seeing it is, of course, this is just what we get by setting s and t equal to 0. And I'm supposed to be able to set s or t to whatever I want, and it's supposed to give me a solution. So setting them both to 0 is valid. So that's another way of describing why this is a particular solution. Anyway, let me talk about one more thing for this video. So first of all, a square matrix is probably what it sounds like. A square is a rectangle where the sides are all the same, and matrices are kind of like rectangles. They have height and width. So a square matrix has the same height and width, so it's the same number of rows and columns. A square matrix could be either singular or non-singular. We say it's singular if the homogeneous system that you get by sticking zeros on the right. So the homogeneous system I would get is like, I would just copy this down, but then there would be a vertical line with zeros on the right. If that homogeneous system has infinitely many solutions, then we say that the original square matrix is singular. Of course, the other possibility is that that homogeneous system has only one solution, and in which case we say that the matrix is non-singular. Okay, so let's see whether these are singular or non-singular. First of all, here's the associated homogeneous system. And let's do this. I would like to see a 0 here, so I do this operation. So 0. 4 minus 3 times 2 is negative 2. And then if you have zeros on the right, this is always going to be 0. 0 minus 3 times 0 is, of course, 0. So I've got it in echelon form here, so I can stop. So let's assume my variables are like x1 and x2, let's say. So this bottom tells me x2 is 0. And then if I plug that in here, that's also going to tell me x1 is 0. So I got just one solution. There's no free variables. There's just the solution that there always is. For a homogeneous system, you always have this solution where the variables are all 0. This is just a question of, can you have more? And for this one, you can't. So we say non-singular. Let's do this one. I put my zeros in there. I like having a 1 on top. I would like to have zeros underneath, so I'm going to use my 1 to get my zeros underneath. So I'm going to subtract 2 from this, and I'm going to do row 3 minus row 1 to kill this one. So nothing happens to my top row. 2 minus 2 is 0. 1 minus 2 times 0 is still 1. Negative 1 minus 2 times 1 is negative 3. And the right-hand side's always just going to stay 0. So let me do the third row. 1 minus 1, 1 minus 0, negative 2 minus 1, and 0 minus 0. So at this point, we can start to see what's about to happen. Look at my bottom 2 rows. They're the same. What's about to happen is, I can still go through the motions, but I can see how this is going to work out. I like having a 1 here, but I would like a 0 underneath it, and so I'm going to end up doing row 3 minus row 2, but I can see that that's just going to make this all zeros. So what that means is that we have a free variable. So this variable is leading because it's leading in this row. x2 is also leading because it's leading in this row. x3 is not leading in any row, so this is free. If you have a free variable, you're going to have infinitely many solutions because your free variable can be anything. Of course, I could keep going if I wanted to write my solution in terms of S and T like we did on the previous example, but if all I want is to answer the question, then right now I can say that this has infinitely many solutions. Just by the fact that it has a free variable at all, it has infinitely many solutions. So we would call that singular.